So we're going to talk about volumes of revolution by cylindrical shells. We've already had a couple of videos on discs and washers. So now we're going to look at that second method that we mentioned in those videos called cylindrical shells. And essentially what we do is we use cylindrical shells if the cross-sectional area is difficult to find. So we talked about cross-sections being circular, but if it's hard to find because f of x minus g of x is not necessarily nice, for example, so the top and bottom functions in discs and washers, and if you're not sure what I'm talking about, you can go watch those videos, but if the top and bottom functions aren't always the same and you have to split them into different integrals and things, it sometimes is easier to do cylindrical shells, or when you do discs and washers and for some reason you can't integrate the area. So something happens that the area is difficult to integrate, we can use cylindrical shells instead. So you have to kind of understand what it is. And essentially what we're doing, and I say here to refer to a diagram, if you have a textbook that is an Anton calculus textbook from a long time ago, you will be able to go to that page and see that figure. But essentially what cylindrical shells is doing is if I have an area like this, and let's say this is my x-axis here, this is my y-axis, and I want to find this, but let's say I want to go around the y-axis. So it's difficult sometimes to find out what the area is that I'm rotating in those things, but what a cylindrical shell does is instead of going around and making a circle like that, it goes around this way. So essentially you think of a line and then it rotates all the way around the axis and comes back around. And it does the same thing on the top. And so what you're forming, and that's a poor drawing, is a cylinder. And then you do it with another line that's slightly bigger. And again, these drawings are getting worse as I go, but there's my bigger circle cylinder. And then I have a bigger circle cylinder after that. So the circles keep getting bigger as you go out until you go to the final one, and they're smaller inside. But essentially what you end up with is a number of cylinders, one inside the other. So that's why it's called cylindrical shells, because we're trying to figure out what's the cylinder of each of these small things. So we're making a cylinder, but it's hollow inside, basically. We're just making a number of them and putting them inside one another, just like those little dolls you can buy, right, where you pull one out and there's the next one inside and it's kind of going in like that. It's kind of like that with these cylinders. So that's conceptually what we're doing. We're creating a whole bunch of cylinders, and then we're adding up, we're integrating the area of those cylinders. So the area of a cylinder then becomes important because we're going to use cylindrical shells. So the area of a cylinder is 2 pi r h. So that's 2 pi x f of x. Now, where did the x and the f of x come from? Okay. Where they come from is, if you imagine this is my r and this is my h of my cylinder, if I roll that out, I get 2 pi r, right, and then h. So in my context, if you think about this distance is x, if you imagine that there's a coordinate system right here, let's say, this is x, and this is f of x, whatever the height happens to be. So if my cylinder's here or here or here. So this 2 pi r h, okay, which is the surface area of a cylinder, gets replaced with the r becomes x, because that's the distance I'm going out from 0, and the height becomes f of x. So that's where that x and f of x are coming from. Okay. But you will notice that when we're doing x, we're revolving it around the y-axis because we're making vertical lines go around. Instead of rotating this way, where you're kind of going around the x-axis like that, now you're going this way. You're making a cylinder by going out and around and back. Okay. So when you're with respect to x with cylindrical shells, you're actually going around the y-axis. And if you want to go around the x-axis, then you need to make your cylinder this way. So you make it horizontally, and then you rotate it around, and it creates that cylinder. Okay. So this formula can also be applied to y. In other words, you can have 2 pi y f of y. Once you have the formula, the application of it is pretty straightforward. You just have to figure out what your function is, basically, because that x always stays there. Then you need to know your boundaries and your function. So it's very similar to discs and washers in that sense, but it's just a slightly different take on it. So if you recall from the disc and washers video that I put up, we did this question, but we did it around the x-axis. So now I'm saying, what if it happens if I want it around the y-axis? Okay. Well, if we don't do it around the y-axis, if we did it the way with discs and washers, the way we had been, you would have to figure out the front function, like this. You'd have to draw this line here, right? So the front function from right there down is 4 minus 1, and then the front function is 4 still, but after that is root x. And so it becomes a little bit strange to try to find it with discs and washers, okay, because there's this space as well, and so it's hard to, so you have these difficult integrals if you were going to do it with disc. Now, it's not to say you can't, but I'm going to show you with cylindrical shells it's much easier. So with cylindrical shells, all you have to do is say the equation, the function is root x, and we're going to go from 1 to 4, because it tells us that. So we plug in 2 pi x root x from 1 to 4. I take the 2 pi out, and that 2 pi stays out because it's a constant, so it's not affecting the integral. And then x times root x becomes x to the 3 over 2. I integrate that, becomes 2/5 of x to the 5 over 2, and then I'm going from 1 to 4, so I plug in 1 and I plug in 4, and I subtract them, and I end up getting my answer. And again, those are the algebraic numeric manipulations. You don't have to do all of that. If you look on your calculator, if you have a graphing calculator that's capable of taking integrals, then use it, especially for this kind of calculation. But I would suggest, like I did with discs and washers, leaving out the pi, I would leave out this 2 pi until the end, and then whatever your result is on your calculator, so it was 62 over pi here, then multiply it by 2. 62 over pi, sorry, then multiply it by 2 pi. So that's cylindrical shells. Now we can modify that as well, just like we did the other one. So if you have something like this, it says use cylindrical shells to find the volume of revolution generated by rotating the region in the first quadrant that's bounded by y equals x and y equals x squared. So we take our line here, x is the bigger function, x squared is the smaller function. So what we do with these, just like we did with discs and washers, particularly with washers, is what we were talking about there, is we just subtract. So we take the top function minus the bottom function, and we rotate that around, and that gives us our volume. So we're going to go the 2 pi and the x stay there, but what we do is we just go top minus bottom. So we go x minus x squared, and we're going from 0 to 1 because those are the intersection points. You notice it didn't tell us there. It just said it's bounded by x and x squared. But in order to find that, you would have to say x is equal to x squared. And the only time that's true is if x onto x minus 1 is 0. Okay? If you bring that x over there. So that means that x is 0 and x is 1. Those are your two possible intersection points. All right? So that's where I'm getting the 0 and the 1, and then once you've set that up, you have to multiply it in, the x in. I leave the 2 pi out. I always do that because it's a constant and because pi is irrational. So it doesn't make our lives nice if we don't. But we multiply the x and we have x squared minus x cubed. And then from there you just integrate. And again, I'm confident in your ability to integrate. If you have a calculator that will do it for you, then use your calculator to do that part in terms of the algebraic stuff. But again, leave the 2 pi out, leave the 2 pi out, and then when you get the 1/12 at the end, then multiply the 2 pi in and get pi over 6. So that is the concept of cylindrical shells. Now, you'll notice both times that we went around the y-axis. So what happens if I want to go around the x-axis? So here's an example. Use cylindrical shells to find the volume generated when the region R under y equals x squared over the interval 0 to 2 is revolved around the x-axis. So if you're going to go around the x-axis, the difference with cylindrical shells is around the x-axis, now everything has to be in terms of y. So it has to be x equals something. So if you look at the x equals, or the y equals x squared here, then what I've done is I've said, okay, if y is x squared, then x is root y. It should be plus or minus, but I'm looking at the positive one, okay? And then I have x equals 2 because it's on the interval from 0 to 2, and I have x equals 0. So this is what I'm talking about. And then I draw my line. It's already drawn in here. But the front function is 2. The back function is root y. Okay? So I'm going to go integral from 0 to 4 because the y value is 4 when the x value is 2. All right? And then I'm going to go 2 pi y. That's my 2 pi x f of x. Well, it's 2 pi y now because it's in terms of y. And then f of y is my front minus my back, so 2 minus root y. And then again, you integrate from there. And I won't bother doing that part. I think you can handle that. But when you do that, you end up with 32 pi over 5. And if you do it with discs, just to show you the previous method, and I'm going quickly because the time is almost up, but discs would say take the top minus the bottom. The top is x squared, the bottom is just the x-axis, so you would just be integrating x squared squared, right, if you're doing it with discs. And you go from 0 to 2. And what you end up with is exactly the same answer. So they both work. Sometimes one is advantageous, sometimes the other is advantageous. Often we use discs if we can because it's a simpler formula, but if we can't or it's more complicated, then we use cylindrical shells. So we'll leave it there. We'll do more examples on your own. But that is the concept of volumes by revolution with cylindrical shells.